Hey friends, I'm Shaptarshi. I just completed my Masters in Chemistry from IIT Kanpur. And in this video series for IIT-JAM exam, I wanted to cover all the different types of numerical problems that come for physical chemistry. And by doing those problems, I'll be explaining the concepts as well. In physical chemistry IIT-JAM, 90% of your questions will be numerical based. So it's very important. And just like this video, I'll be making similar videos on different physical chemistry topics as well. So with that, let's get started with this one.
So I hope your preparation is going fine, and even if it's not going fine, you keep studying and hopefully you will crack the exam. Today we'll study about solid state. In this video, I'll tell you all the basics, fundamentals that you should be knowing, and in the next video we will solve the numericals, which is very important. Okay, so this will be really a very good, quick, effective revision, and I studied like this only during my preparation. Okay, so the types of unit cells. Number one, the most important thing, as you guys know already, I won't take too much time, about simple cubic cell, body centered and face centered. What you should be knowing is that simple cubic cell has 7 types, and this question actually came in this IIT-JAM exam, I believe. How many crystal systems were there and how many Bravais lattices were there? So there are 7 crystal systems and there are 14 Bravais lattices. And how is it that so? So these are the 7 crystal systems that you can see, the cubic, tetragonal, orthogonal. These are the 7 crystal systems, and these have many lattices. Suppose this orthorhombic, this has 4 lattices. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So ultimately there are 14 lattices and 7 crystal systems. This is a very important thing that you guys should be knowing. You guys should also know the axial distances and the axial angles. And there's a trick to remember this thing, for which one you have what the conditions are, because sometimes they do ask these axial distance and axial angles. Many people skip it because they think it's too tough, but there's some tricks to remember it, and I will tell you right at the end of today's lecture. You should also know that I will come to this later about NaCl, because NaCl is very important and questions come from it many a times. So with that, we will see, we are only seeing the most important things over here. Okay, so in this simple cubic, so this table I really liked because it captures everything. So as we know, like in corners, the atoms can be present at the corners, at the body, and it can be present at your faces. If it is present at the corner, it will contribute 1/8. Sorry for that, it will contribute 1/8. Okay, if it is present at the body, it will contribute total 1. Okay, and if it is present at the face, it will contribute half to the total atom count, to the total. Okay, and over here what we see in cubic systems, if you guys remember, we have 8 atoms in the corners, so it will contribute 1/8, and all these corner atoms will contribute what I just said, 1/8. So for simple cubic, body centered, face centered, it all contributes 1/8. So and in a simple cubic, we do not have anything at the face, nor we do have anything in the center, right? So the total atom count is 1. In body centered, the total count is 1 for the body, that is in the center of it, and 1 that comes from the corner. So the total atom count is 2. In face centered, 1 atom comes from your corners, the total contribution that comes, and 3 atom contribution comes from the faces. And so the total atom count we have is 4. This is very fundamentals and you should be knowing this. If you don't know this about solid state, then it will be very tough for you in the exam. Okay, we'll go into and look at a bit details also right now, and we will see. Okay friends, so now let us look at this table. This is a very important table. You should know all the packing fractions of all the, whether it's 52.4%, 68 or 74. If you don't know what's packing fraction is simply, it is the volume that is occupied by atoms divided by volume of unit cell. Volume occupied by atoms divided by volume of unit cell. Normally derivation you don't need to know it in the last minute, but you should know the values. Values are very much asked in these exams. And this is very important, the radius of the atom in respect to the edge length of the unit cell, right? And how does this come? I'll just give you a small explanation for this. I have a picture for it. So over here you have this picture of, this is for FCC. Okay, look at this picture. This is for FCC, face centered cube. And we know that, as I had already said, that in FCC there are 6 faces, and each of this face have your 6 atoms, which contribute total to 3 atoms, because face atoms contribute half, right? So just like one of the faces I'm showing over here is that there's an atom over here, and when, so suppose this is R is the radius of this atom, R, this is R, this is R, and this is R. So total what happens? There are 4 R's, so 4 R's. And the unit, when you look at this lattice, so what is this? This is your diagonal, and diagonal we know is equals to root 2 of A, where A is the edge length, right? So this is how it comes. Then R will be root 2 by 4 A, which will nothing be but root 2, it's 2, and 2 by 2 into 2, so this will become 2 root 2 A. Okay, so did I do it correctly? So this will be 2 into 2, and so the root 2 will cut, and this will become 1 by 2 root 2 A. Okay, yeah, that's it. Don't skip steps. Okay, sometimes we like calculate in our mind and we write it down, but we don't change the values. So don't skip the steps. This is very important actually. I also told myself before giving the exam to write all the steps. Take more time, but what's the point of getting a wrong value? So the value we got was 1 divided by 2 root 2A. So, and what is over here is the C, the same value is over here. So similarly we did for BCC and SCC. I'll just give you a small explanation for BCC and SCC also, how it came with this only. See, BCC is totally similar, except the fact instead of a body like a diagonal, we have this body diagonal. So it goes from the center of the cube. It's not one of the faces. Okay, so this is like a cube, and for FCC we have one of these faces. Let me just take this black color, is one of these faces, but in body diagonal it's in the center of this cube. So the diagonal will run throughout the cube, like, okay, like from here to here. So let me, if I like, so this whole body diagonal is not root 2A, but it is root 3A, and it will be similar 4R. So over here what we can say, that R is equals to root 3 by 4 A. For SCC what happens is, SCC, so there you have nothing in the face, nothing in the body, you have all in the corners. So what happens over there is that in the corners only the atoms meet. So suppose I'm just drawing one of the faces. So suppose this is one of the atoms, and it's a 3D picture, so I'm just drawing one of the faces. So this is A, and this is also, so this whole thing is R, so this is 1R, and this is another R, so this is equal to 2R, and this whole length is the edge length, so 2R, which is equals to A. So R is equals to A by 2. So remember these values, and let us check whether we are on the right track or not. And yep, so R equals to A by 2, R equals to root 3 A by 4, and this is just diameter they have made, which is R into 2. Okay, there's nothing special about it, but these values are important, guys, and you should know the relation between the R and the A for each of these 3 cases, and I've told you how it's done. If you cannot understand, just pause it and watch the video one more time so that you can understand. That's the beauty of videos, right? You don't have to say it again, you can watch it again, but this is important. Okay, and because solid state is such a big chapter, you cannot revise everything at the last moment, so I'm just telling you the most important things and how to recall the things at the last moment. Okay, so now we come to this most important, density, because this is a part, this part in Bragg's law, from where the most numericals will come. So this is nothing but the mass by the volume, and this is the formula. You should know how this formula comes. Why? Because sometimes they change some parameters, and if you don't know this derivation of this formula, it will be a bit tough for you. They might give some other type of mass, and you have to get it to this particular unit or whatever. If you don't know how the formula was derived, this will be a bit problematic. Derivations are not important for every formula, but for this, from my experience, I'm saying this derivation you should know. So, and it's easy also. And when derivations are tough, the examiner themselves don't expect the students to remember it, at least for the your entrance exams. And so over here we have the mass of unit cell divided by the volume of unit cell, and the mass of unit cell is given by number of atoms and your mass of one atom. So suppose this mass of one atom is m, so I have said number of atoms is z and mass of one atom is m. So this m, which is mass of one atom, is equals to atomic mass divided by Avogadro's number. Why are we dividing it by Avogadro's number? Is that Avogadro's number, as we know, it is 6 into 10 to the power 23 atoms for atoms, and for molecules it can be that number of molecules, but here we are seeing for atoms. Here we are looking at only one atom, right? Therefore it's important to divide by Avogadro's number. Therefore the atomic mass, this will be given, most probably this will be given, and Avogadro's number you should be knowing, it might be given in the question paper. So this is the part where we get the mass, and now what is remaining is that we have to get the volume. So volume of unit cell is AQ, where A is the edge of unit cell, right? And we just normally replace all the values. So what we get from here is mass is m by Na, and mass of unit cell, that is number of atoms into your Z into m by Na. And this, so this portion comes from the numerator, this portion is coming from the numerator, and this portion is coming this portion is coming from the mass of unit cell, and this portion is the volume, right? Okay, so this Z will change depending on whether it's SCC, BCC or FCC. So SCC, Z will be 1, for BCC your Z will be 2, and FCC your Z will be 4. Value of Z, the number of atoms, which we just saw right now in that table. That's why the table was very important. Okay, and now I believe we are coming to this form of radius ratio. It's radius, oh no, it's the radius of tetrahedral void and octahedral void. This is also very important. And so the whole logic of this is not really asked in the exams. About maybe conceptual questions might not be asked, but they might give a 1 mark numerical about it, because this concept is not that important, but it is cannot be left out also, I will say. So the radius of tetrahedral void, which is, suppose it is r, or so that is 0.225 times of the capital R, where capital R is your radius of particle or atom. Similarly for octahedral void, R is the radius of tetrahedral like octahedral void, and it is 0.414 times of capital R, where capital R is radius of particle or atom. Okay, so the formulas for this you just know it, because in the last moment there might be a question of 1 marks from it. And radius ratio is important. It is the radius of cation by R anion, R plus R minus, and this table is important. Okay, sometimes they ask, and examples, everything about this table is actually important. Okay, and so for what range of radius ratio that we are seeing, let me just take the black color to make more impact. So for what range of radius ratio, it will be coordination number will be this, or the structural arrangement will be what. Okay, so this is many a times asked in the exam, and remember the examples, that especially for sodium chloride and cesium chloride. Okay, these two examples are very important, that the structural arrangement is like octahedral, it's like body centered cubic, coordination number is 6, for this is 8, and the range, remember the range of radius ratio. Okay, similarly just remember for zinc blende also and boron trioxide also. These are the most important examples, especially NaCl and CSCl. There's a trick that I used to remember for this, to remember the ranges of the radius ratio, is that, as you guys know, 15 square is 225. Okay, so 0.155 is so 0.225. So these two things is like a bit correlating. So I believe 15 square was 225 only, if I'm not wrong. 15 into 10 is 150, 15 into 5 is 75, 150 plus 75, 225, yeah. So so this is, and it goes in like, in like an order, 1.555 to 225, 225 to 414, 414 to 732, and 414 and 732 you just remember, and it goes till 1. So that's how remember, and if you remember 1 or 2 times, next times you will remember. Okay, and actually there's, in later when you do research or something, all these values, nothing to remember, you will get on the Google or some things only. No one will ask memory power, but having some knowledge of it will give you an idea to think also for further knowledge. If you have to Google for everything, that will be a bit too tough to do research also. Okay, so some important notes, because solid state is a very big chapter. I'm just taking some important notes of theoretical concepts that you might get. That NaCl is FCC, phase centered cubic, and it is a 6:6 coordination. What does that mean? Is that every your Na plus atom is surrounded by 6 Cl minus atoms, and every Cl minus atom is surrounded by 6 Na plus atoms, and it has this FCC structure. And about diamond is a sp3 hybridization. It has strong covalent bonds. It is hard in your nature. It is a bad conductor of electricity. Graphite, very important. Graphite is very important because all this research about graphene is going on. Graphene is the next big thing coming up in the world of materials. So this has like sp2 hybridization. This has like weak van der Waals forces, and it is a good conductor of electricity. Very important point. It is a good conductor of electricity. And this hybridization is sometimes also asked. Okay, and okay, this F center. Okay, I have seen so many questions about F center, about imparting color to substances. So this is caused by two things. One can be a metal excess defect due to anion vacancies. So there might be some anion vacancies. As you guys know, there are some defects in crystals. It might be stoichiometric in nature. It might be non-stoichiometric in nature. If you have time, do read it up, and it's not tough to remember also. It's quite easy. The Frenkel defect, the Schottky defect, it's not very tough to remember. Okay, Schottky, I believe. But the important things I'm telling you over here, which have very high chance of coming in the exams, that because there are so many defects and so many properties as well. If you cover the whole thing, I mean, I don't know how you guys will revise if you guys cover the whole thing. So anyways, the metal excess defect due to anion vacancies is very important. Is that if the anion, that place is vacant, and so to make up for it, the electrons get trapped in the anion vacancies, right? And because of this electron is trapped, there is some F centers created which impart color, right? The examples for this also very important is that LiCl and KCl. Okay. So examples you should know. And one more case where this F center thing comes up is that metal excess defect due to interstitial cation, and to make up for this extra cation is neutralized by an electron at an interstitial site, and this electron again imparts color, which again is the F center, and imparts color. So this can be called at ZNO, like one example. So remember, there are two cases for this. One is metal excess defect due to interstitial cation, and one is your metal excess defect due to anion vacancies. Both of them can impart color, and remember the examples for different cases. Now we come to the most important part of solid state, that is your Bragg's law and Miller indices. First of all, what is Miller indices? Miller indices are reciprocal of x, y and z intercept of a plane. I'll give some examples because Miller indices, this portion is important. Okay, so suppose for this we have I have drawn an axis. It's a bit slanted, but you guys can get the concept. Okay, no need to see my presentation. As long as you get the concept, that's the main thing. Okay, so x, y, z, you guys get this thing. And so over here we have this crystal structure, unit lattice, and it is a unit cube. What does unit cube means? It means that every length of it is unity. Like in the x direction it goes till unity, in the y direction goes till unity, so it goes till 1. And as we see over here that in so this shaded is in the front region, right? Comparison to this shaded, this y axis, this z axis is parallel, and its z axis and this x axis is being intercepted at 1. So if it is parallel, the intercept is infinity, right? And x intercept is 1. Miller indices is not that. Miller indices is the reciprocal of it, so it will be 1, 0, 0, right? Let us see one more example for it. Is in over here. This is a very good example. So I have given the points. So this top point is 0, 0, 1. This point over here, you have to see, is 0. The y-intercept is 1 by 3, and again 0. And again I have given the points over here. This is 2 by 3, 0 and 0, right? So the x-intercept, y-intercept, z-intercept you are getting from those points. Miller indices will be the reciprocal of it. Now what we get is this, but this is not the Miller indices. Miller indices has to be an integer. And what integer? The lowest integer possible. So to get the lowest integer, what we need to do over here? Multiply by 2. Simple as that. We get 3, 6, 2 plane. And this is also called your HKL plane, right? So Miller indices are represented by your HK and L plane. HKL plane. So Bragg's equation. So now we'll come to this most important part of Bragg's equation, because a lot of your numericals will be actually based on your Bragg's equation. And Bragg's equation is a fundamental equation which gives the relation, between your wavelength of X-rays and interplanar, the distance between the two planes, and the angle of reflection, relation between your lambda of X-rays, and this XRD thing is actually very much used in research, and it is I have heard it's not very easy to operate. You have to learn this XRD for like 1 to 3 years before you operate on your own. So it looks so simple, but operating it is not easy, and it is very costly also. All these things, relation between lambda, wavelength of X-rays, your the theta, which is the angle of diffraction, and your interplanar distance d. So over here we are going to see the formula, and the formula is your n lambda 2d sine theta. That is the formula used. And what does the formula mean? N is the order of diffraction. It can be 1, 2, 3, 4, any whole number normally given, and wavelength of X-rays is lambda. Theta, d is the distance between the two planes. So I believe you guys can see over here. I'll just show the picture as well. And theta is the angle of diffraction. Okay, it can also be called as grazing angle or glancing angle. Many people sometimes they give the grazing or glancing angle, and many people think, oh, what is this? I don't know. So this is actually 90 degree minus the incident angle. Okay, you don't need to do any calculation. Okay, sometimes in physics we used to do in before that to find incident angle, now we don't do minus 90, but this theta is actually the grazing angle. Okay, so you don't need to do any calculation over here. This is I just told for this concept. And so I'll just, where is this mouse? So over here, if you see, if I draw this normal, I think this is called the normal. In physics we learned. So this, if we see, is the theta, which is the incident angle, the 90 degree minus theta will be this portion, which is the theta, right? This is 90 and this is 90 degree minus theta. So this, our theta is the grazing and glancing angle. Again guys, I'm repeating, don't do any calculation. If it is written grazing or glancing angle, just don't be scared what it is. You have to just put that value of theta in the formula. That's it, done. Your d is the distance between two planes. This is given a, this should be d actually, and your lambda will be given and n will be given. In the next we will see some very good examples which will really help you in your exams. Some very good examples I picked out especially for IIT-JAM level. Okay, so I told you guys that I will tell you how to remember the formula for this portion, and I will just tell you. So this is the last one. So the formula is see Tom there. I got this from YouTube only. So it said see Tom there, and Tom, you can remember this Tom and Jerry Tom. C means C, you know, you write the C part, and there is there, but you just write THR, and accordingly you know, you just should know what C, T, O, M, THR is. This is very easy only. Remember the tetragonal comes before triclinic because both of them are T's, and the rest you can fill it up if you don't. If you know, cubic. The problem is you don't know in what order it is. You guys know the names of the crystals, obviously, right? You don't know in what order it is. Now, the thing about this formula I liked is that it's very symmetrical. In between all these three you have is, so just take a screenshot before I mess up the whole thing with more marking. Take a screenshot. So in between all these things you have is A not equal to B not equal to C. Okay. Above this you have A equal to B not equal to C. Below this you have A equal to B not equal to C. And above this you have A equal to B equal to C and A equal to B equal to C. So this is very easy to remember. Like it is so symmetrical in nature. And on this angle side we have that alpha equals to beta equals to gamma for the first three ones. And then you need to remember that alpha, you just remember all these. So these things are not really that much asked as much as this distances. But for these you want to remember, you can remember like for the last two ones you see that alpha equals to beta equals to 90 degree. These things is constant for the last two. And for triclinic, if you remember the triclinic, both these things are not equal to, A not equal to B not equal to C, and alpha not equal to beta not equal to gamma. And the only other option that is remaining is in the monoclinic. So therefore I believe that this formula is the best way to remember. Like it's called mnemonics. It's the best way to remember because it is the most symmetrical. Because before I used a different method which was not that good as this one. This is, I believe, a more better method, and it is more symmetrical in nature. So with this we have covered all the important sectors for this chapter of solid state, and